Well, so we have come almost to the end of the multiphase flow course, and till now you have studied the different flow patterns, the different analytical models, flow regime based models, boiling, condensation, so on and so forth. So, I felt, or rather we felt, that the course will be incomplete unless we discuss some aspects of experimentation in two phase flow. What are the specific challenges which are connected with the different measurement techniques in two phase flow? Maybe the same thing we are measuring, say the pressure drop. We measure pressure drop for the case of water flowing through a pipe, or in gas filled lines also. We measure pressure drop for two phase flow also. What are the special problems that we feel when we are measuring different parameters of two phase flow? We will be see, since I do not have much time, what I have decided to do is, we will first take up the most common parameter that has to be measured in fluid flow, that is the pressure drop. You already know pressure drop measurements, how it is measured in single phase flows. So, we will just see what are the added challenges, what are the added difficulties while measuring two phase pressure drop, and naturally how to minimize. We cannot eliminate the difficulties completely, how to minimize the difficulties, and which technique we will be adopting for different flow situations. Next, since I do not have time, I will be not taking heat transfer coefficient, etc., etc. Next, we will take up one particular parameter which is unique to two phase flow. The first important parameter which has to be measured for two phase flow is void fraction. Unless you know the void fraction or the in situ composition of the two phases, we cannot do anything. So, I will be going for the void fraction measurement, and after void fraction measurement, probably I will not be having much time. I will be taking up the detection of flow patterns, because once flow patterns are detected, once you know how to estimate the void fraction, then more or less with this particular void fraction data, considering the particular flow pattern which is prevalent, we can predict the pressure drop, or we can at least perform analytical models to predict the pressure drop, and we can also perform analytical analysis in order to predict the heat transfer, mass transfer coefficients, the chemical reaction kinetics, etc., for reacting systems for two phase flows. So, therefore, it will go on in this way. First, we will be discussing pressure drop measurements during two phase flow through a pipe. Next, we will take a void fraction measurement, or the measurement of the in situ composition of the two phase mixture flowing through a pipe, and after that we will be spending about two classes on void fraction and about 1 or 2 classes on detection of flow pattern. More or less the techniques adopted for void fraction measurement as well as the flow pattern detection should be the same. Both of them should work on some particular principle which is based on the difference in any particular physical property of the two fluids, isn't it? But in one case we need a quantitative estimation, in the other case we need a qualitative estimation. Okay. So, we will be doing void fraction in greater details. Most of the techniques probably we can find out, we can use for flow pattern detection. Remember one thing, for void fraction usually it is a steady state sort of a thing, and therefore, steady state response is sufficient. For flow pattern, the time variable response is needed. Based on the time variable response, we will know what is the prevalent flow pattern. Okay? And then of course, just from seeing the time varying response, it is not sufficient. Maybe we have to perform some statistical analysis. We will be just discussing those particular things during estimation of flow patterns. Now, let us start the measurement of pressure drop. A very simple technique. You know what you do, simply there is a pipe standing, there are two pressure tappings, you connect the two pressure tappings either to any particular pressure your measuring device, it can be a manometer, and if we need some better more sophisticated device, we will go for transducers, you already know that. Okay. You also know the principle of measuring pressure drop using manometers. We will just develop that, or rather we will just derive that particular portion, and then just so that you can understand why measurement of pressure drop in two phase flow presents certain additional difficulties. Now, I will just like to redraw the figure once, it will be clear to you in that particular case. So, therefore, in this particular case a two phase mixture is flowing. Okay. It is a two phase mixture which is flowing. Now, this is connected to a manometer line. So, this is connected to a manometer line, the pressure here is P 1, the pressure here is P 2, this two phase mixture is flowing, it is having a density say rho T P we can put it, and here the manometer level is somewhere here, it is somewhere here. So, if we take this as the datum, then we find that this is going to be say Z 1, where Z is the vertical distance of different points from the datum that we have selected. This will be say Z 2, this will be say Z 3, and this is going to be Z 4 say. Okay. Now, in this particular case, how to find out P 1 minus P 2? How do you think that we can find out P 1 minus P 2 in this particular case? It is simply, suppose we would make a force balance across the section say A prime. Okay. Suppose we make a pressure balance across this section A prime. So, what do you find? The pressure at A, what is it? It is P 1 plus Z 3 minus Z 1. I think there are some mistakes here. So, you just follow my derivation, or it is all right probably, I do not know. G sorry it is all right, Z 2 minus Z 1 G rho C, this is equal to P 2 plus Z 3 minus Z 1 G rho M, okay, plus Z 4 minus Z 3 G rho C. Just let me check up. This is P 1 plus Z 2 minus Z 1 G rho C. This is equal to P 2 plus Z 3 minus Z 1 G rho M plus Z 4 minus Z 3 G rho C. Isn't Z 4 minus? Is it Z 4 minus? It's going to be Z 4 minus. Yeah, it's all right. Okay. So, therefore, so from here what do we get? P 1 minus P 2, if you just rearrange it, what are you going to get in this particular case? Your P 1 minus P 2, this will be equal to, we are just rearranging it, Z 3 minus Z 1 G rho M plus Z 4 minus Z 3 minus Z 2 minus Z 1, isn't it? Yeah, Z 3 minus Z 1 G rho M plus Z 4 minus Z 3 minus Z 2 minus Z 1. Sorry, here also it was Z 2 minus Z 1, very sorry. The basic was, it was sorry, it was Z 3 minus Z 1 G rho M, Z 4 minus Z 3, it is all right. Z 3 minus Z 1 G rho M plus Z 4 minus Z 3 minus Z 2 minus Z 1 G rho C, correct. Just from the typical force balance we have got this particular part, or in other words this can be rearranged and written as P 1 minus P 2, this is equal to Z 3 minus Z 1 G rho M minus rho C, just rearranging this, plus Z 4 minus Z 3 G rho C. Agreed? Now, you see when P 1 equals to P 2, what should happen? When P 1 equals to P 2, normally what do you feel? When the two pressures are the same, the two manometer levels should also be the same. But from your mathematical expression, do you get that? For P 1 equals to P 2, what do you get in this particular case? Tell me. Just do it and tell me when P 1 minus P 2 equals to 0 or when P 1 equals to P 2. Under that condition, what do you get? It is going to be Z 3 minus Z 1. This is equal to minus of Z 4 minus Z 3 rho C by rho M minus rho C. Which one? P 1 equal to P 2? Oh, previously? which one, P1 minus P2 equal to this one, do you mean to say Z3 minus Z1 G rho m plus Z2, it's all right. Or just check up, it is simply your mass balance, it is simply a force balance, nothing else. Okay. So, therefore, what do we find from here? If P1 equals to P2, then in that case what do you find? You find that normally what should have happened, your both the mercury levels should have been on this or rather both the manometer levels should have been the same, or in other words Z3 should have been equal to Z1. That you have observed when you have measured the pressure drop for water flowing through pipes. Isn't it? It is something very common that you have seen, but from the force balance you find that well no, Z3 minus Z1 does have a value. Okay. And this particular value, this when P1 equals to P2, the difference which you find, the Z3 minus Z1, any idea of what this is called? For equal pressures, the difference which you find, which has to be considered when you are measuring pressure drop, what is this called? What is this called? Have you heard of something like the offset in process instrumentation? So, this is the offset on manometer. Okay. So, this offset have to be kept in mind, that this offset has to be compensated or taken into consideration when we measure the pressure drop. Okay. So, on what does it depend on? It depends on the vertical distance between the tappings, and it also depends on rho c, is not it? So, this we find it depends, the offset, it depends on vertical distance between tappings and on rho c, it depends on these two things. What else do we observe from here? We observe that when there is no flow, in absence of flow, what do you observe? What happens? So, in that particular case we find that just the hydrostatic head difference should contribute to the pressure difference, yes or no, is not it? Or in other words, when there is no flow, then in that case your P1 minus P2, this should be equal to G rho Tp, the two phase fluid, into Z4 minus Z2, is not it? And what is this equal to? The manometer, in absence of flow, the pressure difference is this, and what about the manometric difference? We simply substitute the expression of P1 minus P2 from here, and then we can equate this particular expression with the expression of P1 minus P2 here, and then we can get the manometric difference in this particular case. So, we for finding out the manometric difference, what do we do? It is G rho Tp Z4 minus Z2, this is equal to Z3 minus Z1, the manometric difference, plus it should be Z4 minus Z2 by, just do the derivation once, it is going to be clear to you, into G rho C. Or in other words, from here what do we get? We get the distance between the tapping lines into rho T minus, rho Tp minus rho C, this is equal to Z3 minus Z1 G rho m minus rho c. Or in other words, when there is no flow in the pipe, okay, for no flow in the pipe, for no flow we get Z3 minus Z1, which is nothing but the manometric difference. That means, when there is no flow, when simply the two phase mixture is standing there, we should get Z3 minus Z1 equals to Z4 minus Z2 rho Tp minus rho C by rho m minus rho C. Is it clear to you? The derivation which I have done, is this derivation clear to you? Fine. So, therefore, from this particular thing, what do you deduce? If you observe the final expression which I have obtained here, From this particular expression, what do we deduce? You have observed in laboratories when you have studied, when in a vertical pipe simply water is standing, okay. We have connected it to your tappings, and then naturally the tappings are filled with water, and then probably we have a mercury manometer or a carbon tetrachloride manometer. So, when no flow occurs, we find that both the levels are standing at the or rather both the levels of the manometric liquid are the same in the manometer. Very common, you see this and then we start the experiment. Mostly the offset is so less that we can ignore the offset. Usually for your purpose it has been observed that, is not it? But in reality we find that when there is no flow, then this manometric difference, it is a function of the distance between the tappings. This is a distance between the tappings, and it also depends upon some density differences. Okay. What are the density differences? They are the density of the fluid which is flowing through the tube minus the density of the fluid which is filling up the tapping lines. Okay. So, if you observe the slide which I have here, we find that when there is no flow, just this slide which I have there, we find when there is no flow, then in that case the manometric difference here, it will depend upon the distance between the tappings, and it will depend upon the difference in density between the mixture or between the fluid which is flowing here and the fluid which is filling up the lines, divided by the density of the manometric fluid minus the line fluid. Agreed? Now, so you understand when there is only water filled up here and there is water here, then in that case the density of the fluid inside the tube is equal to the density of the fluid in the manometer lines, or in other words the rho here becomes equal to the rho here, and that explains why Z3 minus Z1 becomes 0 under that condition. Okay. So, we always every time, I do not know whether this you have been told in your during your experiments or not, it is a norm to first find out that you have to first fill it up with water, then see that both the levels of the mercury are or both levels of the manometric fluid are in the same level. After that you start the experiments. But when we have two phase flow, we find that in this particular case, under most of the circumstances, the density of the fluid inside the tube will not be equal to the density of the line fluid, and therefore, there will be a difference in the manometric or rather in between the two levels of the manometer when even when there is no flow inside the pipe. So, this is the first hitch we come across. Why do I call it a stumbling block? Because we find that therefore, in order to measure the pressure difference here, what do we need? We need to know the density of the fluid which is filling up the manometer lines. Now, in order to know the density, the first thing is we have to know the composition of the fluid there, and the other thing is we have to maintain a constant composition. So, there are two things. First, we have to know the composition, then we have to ensure that the composition remains constant throughout the time we have made the experiments, we have made the measurements. That is almost impossible. When suppose two phases are flowing here, just to maintain a constant composition throughout the time, because the composition will naturally be changing with change of operating variables. This is impossible, and once a two phase mixture is flowing through the special lines, there is no way to find out the composition and the density of the line fluid. So, what is the only alternative that we have if we want to measure two phase pressure drop using a manometer or wherever there is a pressure, the lines connecting the manometer or the pressure measuring device with the main tube. The only thing which we can do is we have to ensure that the manometer lines are filled up with a single fluid only. For gas liquid measurements, it can be filled up either with a gas or with a liquid, and we have to ensure if it is filled up with a gas, no liquid enters the tapping line. If it is filled up with a liquid, no gas enters the tapping line while we are doing the measurements. So, this definitely tells you what is the hitch, the stumbling block we have in two phase flow measurements, even when we are measuring something very simple like the pressure drop. Measuring pressure drop in fluid flow is one of the most common things that we do. And even for that you can very well understand where the problem arises. The problem arises that in order to measure an accurate measurement of pressure drop, it needs an estimation of the density of the fluid which fills up the connecting lines between the manometer and the tube or the pipe through which two phase flow is occurring. Okay. Now, if we have to know the density and we have to ensure that the density is constant, then in that case we have to ensure that the fluid or rather the lines are filled up with only one particular fluid, either a gas or a liquid as the situation may be, and not only it has to be filled up at the beginning of the experiments, definitely that you can ensure, you can fill up the lines and you can start. While doing the experiments, can you ensure that two phase flow is flowing here and no amount of the second phase will ensure the tapping lines? Is it possible? So, but that has to be ensured. Okay. So, therefore, what are the major challenges or the special difficulties in measurement of two phase pressure drop? First thing, as I have told you, that moment a second phase enters, there are possible ambiguities in the content of the lines joining the tapping points to the measuring device. These slides I think you can get, is not it? The other thing is, see how does the second fluid enter the first enter the your line. The reasons by which they can enter is, say, suppose the lines are filled up with liquid. Okay. Now, what happens whenever the two phase mixture is flowing, naturally there will be pressure fluctuations. Whenever there are some particular pressure fluctuations, then naturally the manometer has to record it. So, naturally the manometer level will go up and down. Moment this level goes up and down, then what happens, there is some amount of pressure drop created and that causes a sort of pumping sort of action, some sort of a pressure drive which draws the fluid from inside the pipe into the tapping lines. So, this is number one, that changes in pressure drop and movement in the manometer to record it. Then the other thing is, naturally in two phase flow it is a random phenomena. So, there will be pressure fluctuations. Whenever there are pressure fluctuations, this will cause some sort of a pumping action. And the third thing is, it can always happen that for a sudden depressurization, when the pressure inside the line fluid suddenly becomes very less, and maybe we are working with cryogenic fluids or we are working with liquids with low boiling points. Under that condition, following a depressurization, there can be a flashing in the lines, and with that particular flashing a vapor bubble can be formed, say inside a liquid, right. So, therefore, we find that firstly, suppose we have filled the tube with liquid, we have filled the manometer lines with the liquid, everything we have done, then we have started the two phase flow experiments and we are wanting to measure pressure drop. Even when we have filled everything with one particular liquid, but or say with the liquid we have filled it up, moment we start the two phase flow, we find that gas can enter the liquid filled lines by either of these methods. So, suppose we do the reverse, we filled the lines with gases, in that case also liquid can enter the gas filled lines. The reasons will be the same, changes in pressure drop and movement of manometric liquid, pressure fluctuations due to which liquid is pumped inside the lines, and of course, it is a low boiling vapor with a low condensing temperature, cryogenic fluids, there will be vapor condensing. So, either way, whether we fill it up with liquid or we fill it up with gas, we find that the second fluid has every chance to enter. Okay. So, we have to avoid this particular entering. How can we avoid this? One thing is, moment you have filled it up with the liquid, say suppose we have filled it up with liquid, then we have got to have a very efficient liquid purging system. Purging system you have already studied in your chemical process calculation, some subject, is not it. So, we need to have a very efficient liquid, one particular system I have shown here. We need to have purges at different points. See, these are the two tapping points. From there they are being connected. In this case I have shown an inverted manometer. We find that we have got vent lines at different places. Two things have to be done. Firstly, this entire line has to be transparent, so that moment a bubble enters, we find that we can locate the bubble. Then there have to be vents at different positions, so that through these vent lines we can open them, we can remove the bubble, we can close them again. Okay. So, by a very efficient purging system this can be done. If it is gas filled lines also, we can make up a purging system and ensure that there is no liquid inside the line. First we have to locate it. Now, if there is a bubble, firstly definitely in that case we cannot know rho c, that is number one problem. There is another problem also, moment gases enter liquid lines or liquid enters gas lines. What happens? The frequency response changes. Naturally, a moment, say you can imagine when in this liquid filled and a gas enters, naturally that particular gas, it will be oscillating here and there. So, naturally that is going to affect the performance of the manometer, isn't it? So, therefore, these are the two problems which happens. Firstly, we cannot take the measurement at all. Okay? So, this has to be avoided. How? You can take up a purging system. This is one particular thing that we can do. Achha, the other thing which is very important for manometers particularly is, see, since there are rapid changes in pressure and that has to be recorded maybe by the manometric liquid rising, falling, etc., there can be a chance when this particular manometric liquid, it can actually enter the tube through which two-phase flow is occurring. At some times this can be disastrous. Suppose there is a metallic system and mercury enters. So, you can very well imagine how disastrous the situation can be. Okay. So, therefore, this is also another problem, that there can be pressure particularly for slug flow, there can be pressure fluctuations to a large extent, and moment there are pressure fluctuations, there is every possibility that the manometric liquid can enter the tubes, and sometimes this can be disastrous. In fact, I can tell you one thing, when first I had started my PhD, okay, at that time just the first or the second day probably I was working with two-phase flows. Okay. So, that time I was new, naturally I was trying to connect everything, and then I started the two-phase flow mixture, and then the manometer was there and more or less it was showing readings. So, I was trying to adjust everything was new to me. So, I was trying to adjust, I was trying to measure the pressure drop, etc., etc. Suddenly the pressure drop became very high and the manometer lines, they opened up, the entire mercury, it split on me, and the best part was all my ornaments which were there, everything became amalgamated within a fraction of a second. Everything, my earrings, bangles, everything became amalgamated. So, anyhow, that is a different aspect, but this is a problem for manometric liquids. Okay. Now, before I proceed, I would just like to ask you one thing. Can you just tell me, we can have gas filled lines, we can have liquid filled lines. Probably you have never seen gas filled lines as far as I know. Usually we have liquid filled lines, but can you tell me that which lines would you prefer and why? You will prefer a liquid filled line if gas ingress is less as compared to liquid ingress in gas filled lines. So, which particular line will you prefer, considering which ingress is more severe? And if you can tell me why liquid ingress into gas filled lines is more severe, or gas ingress into liquid filled lines is more severe or more serious of problem. Which one do you think? Maybe you can guess something, because you have already always seen liquid filled lines most probably, but what is the reason behind it? Any idea regarding the reason? Try to understand one thing, whenever there is a change in pressure, the gas phase is a compressible phase, isn't it? Now, if it is a compressible phase, then in that case, due to the compressibility, the pumping action will be much higher. So, therefore, for a liquid to enter a gas filled line, it is much more easier than for a gas to enter a liquid filled line. Liquids are incompressible. So, therefore, in this particular case, the pumping action which is caused due to pressure fluctuations, that is going to be much severe. Number one. What is the number two thing? Usually what we do, there is a tube and we are having pressure lines which are maybe glass capillaries or glass tapping lines which are connected to the tubes. Now, in the very beginning I had told you how are flow patterns more or less restricted to a certain number of flow patterns. For air water systems, I had told you that always the liquid will wet the pipe wall. Do you remember this statement? If liquid has to wet the pipe wall, then in that case, due to this capillary action, if it is a gas filled line, then there will be a greater tendency of the liquid to enter, because it is always trying to wet the pipe wall. So, therefore, wetting the pipe wall, entering into the capillary is going to be much more easier in this particular case. So, therefore, liquid ingress in gas filled lines are much more severe and much more serious, and therefore, we usually prefer liquid filled lines. But there are certain advantages of gas filled lines as well. Can you tell me what can be the advantages? If you observe the expression of pressure gradient that I have got, this is the offset, is not it? When there is when P1 equals to P2, this is the offset. Okay. This offset, it depends on rho t minus rho c. So, if rho c is, in other words, yeah, no, this is wrong, I do not have that expression, sorry, this is the expression, very sorry. For P1 equals to, just the thing which I have written down, if you see, yeah. So, for P1 equals to P2, this is the offset. We find the offset depends on what? It depends on rho c. So, if rho c is less, then naturally the offset is going to be less, is not it? If rho c is less, rho m minus rho c is greater, rho c is less. So, on the whole, the offset becomes less. If the offset becomes less, then actually we can measure lower and lower pressure drops. Number 1. Number 2, since in that particular case rho c will be much less. So, therefore, we find that more or less we can get more accurate predictions of pressure drop if rho c is less. Okay. So, therefore, pressure drop measurements can be more accurate and the offset is less for gas filled lines. But the pumping action is so very high and the tendency of liquid entering into gas filled lines are so very drastic that for most of the cases we do not prefer gas filled lines, we prefer liquid filled lines under some, unless some very special circumstances or applications force us to adopt gas filled lines, correct. So, therefore, this was pressure measurement with manometers. Now, as I have told you, usually we do not use manometers. The first problem naturally is, if you have to use manometers, there have to be very long tapping lines, and then the problem of liquid ingress into gas filled lines or gas ingress into liquid filled lines come up, number 1. Then there is also a chance of manometric liquid entering into the your system. So, with all these things, and again there are situations, suppose we want to measure fluctuations in pressure drop. Just by seeing the fluctuations in manometer we cannot do it. Suppose we want to measure pressure response. Okay. So, for these particular situations naturally we would like to go for transducers, that we do for single phase flow also. Okay. So, transducers usually what we have two particular pressure transducers, they are wall mounted pressure transducers, and the signals from the two pressure transducers, they are sent to a system where they are electronically subtracted to give us the pressure drop. So, by doing this, what good have we done? See, the transducers, they are wall mounted. So, therefore, the tapping line content, the ambiguity in the tapping line content, all those things we have done away with. Okay. So, therefore, they are wall mounted and we have a electronic way of subtracting both of them. Okay. So, therefore, this is a good thing, and usually we find that the transducers which we use, they are among the different type of transducers which you must have studied, the different type of transducers, is not it? Potentiometric, strain gauge, capacitance, reluctance, is not it? Eddy type, piezoelectric, etc., we find that for wall mounted signal subtraction devices, usually we have a capacitance type of transducer we use, or a piezoelectric type of transducer we have used. The comparative study I have just shown you that definitely we do, if since we have adopted two particular type of transducers, some will have some advantage over the other. Okay. Usually we never use other type of transducers when we have to do this signal subtraction business. And as I have shown you that capacitance type, its stability is more and its operating temperature, maximum operating temperature is more. At the same time, piezoelectric type, it's much more sensitive and its response time is faster, etc., etc. Okay. So, these are the two types of transducers which we usually use. And what are the advantages? Definitely fast response, electrical output, so that you can record the response and then you can come up later, you can process it, you can find out the pressure drop, you can find out the pressure signal also, the fluctuation of pressure drop with time. So, therefore, there definitely advantages are great, avoids ambiguity in line content, you know all those things. The research would have ended if it would have given us all advantages and no disadvantages. That never happens. whatever you do, you try to adopt anything new just because the previous one had some disadvantages. You want to eliminate or minimize them, but whenever you use something new, it is also always associated with some disadvantages. That is why again we have to go for something new and the research continues. So, for this particular case, what are the main disadvantages? See, if you see this the system, what we do, we measure two signals and we electronically subtract them. Usually both the signals are very large, okay, and such two large signals are subtracted to give you a very small difference. Now, whenever you measure something, you cannot say it is 100% accurate. There will be some errors in any measurement that you do. So, therefore, there is a error in measuring the pressure drop here, or rather the pressure here, there is a error in measuring the pressure here. So, when you subtract these two, then naturally thus difference is very small, and coupled up with the errors, maybe the error introduced may be quite large. It can be one other way also, maybe the errors cancel out, that never happens. The errors, they add up, and therefore, by electronically subtracting, we find that the inaccuracies which we obtain in this particular case becomes much large. Two very large quantities, maybe the error here is small, error here is small, but moment we subtract them, the difference is so small that the error becomes large here. Okay. So, this is the first particular disadvantage. And definitely the other disadvantage is, even see there are no lines, there is no line or there is no connecting line, tapping line between the tapping point and your transducer, but then also this is very much affected by the fluid present near the wall mounted transducer. Even if there is a very small bubble present also, it is so very sensitive, it affects the response. So, therefore, this is another disadvantage, frequency response is extremely affected by presence of gas bubbles near the transducer. So, naturally in that particular case, the more important problem is errors due to subtraction of two large signals. Now, if this is a problem, then what will we do? Instead of subtracting the two signals, suppose we take the two particular signals in one particular device. Say suppose with tapping lines, we connect the two signals to one particular device which has a diaphragm, and the two particular signals are connected to two ends of the diaphragm. Then by the diaphragm movement, if you can measure the differential pressure, that will be more accurate. Instead of measuring this pressure and then subtracting them, this is definitely going to be more accurate. Okay. So, therefore, to minimize the disadvantages of wall mounted pressure transducers, what people have adopted? They have adopted differential pressure transducers. Okay. So, this is nothing very important. They have adopted differential pressure transducers. Okay. What are these differential pressure transducers? More or less there are tapping lines. If I show you the here, what happens? There is a tapping line from here, there is a tapping line from here, they enter into a box, there is a diaphragm into the box. So, therefore, the pressure here and the pressure here, they are different. So, therefore, the thin diaphragm, it starts vibrating, and depending upon that, that is electronically recorded and gives us the pressure. Okay. Now, generally for differential pressure, we found that the transducers which were suitable here, capacitance type and piezoelectric type, they are completely unsuitable. And what is suitable in this particular case? We find that usually the reluctance type and the strain gauge type are suitable. Again, here I have just noted down the advantages and disadvantages of the reluctance type and strain gauge type. Strain gauge type, definitely it is more stable and it has a fast response time, but at the same time the reluctance type, it is much more sensitive. It can give us much more accurate pressures for very low case. Well, so the other thing is, now you adopt the differential pressure transducer. Okay. Now, again if it would have been very good, then again we would not have bothered about anything else. There has to be some problems there. What are the problems? What are the problems that come to your mind in this particular case? Moment we take up differential pressure transducers, what do? Again we are having tapping lines, these tapping lines are connected to the two ends or the two sides of a diaphragm. So, therefore, all the problems that were associated with tapping lines, the problems which I have noted down here, all these problems they should be there in the case of the differential pressure transducer also. But the good part is, see, in the manometer the movement of the liquid is much more vigorous. Okay. So, therefore, this pumping action is much more there. Here the diaphragm it moves to a very small extent. So, therefore, pumping action is not so very high, and therefore, the ingressing of the second fluid into the manometer line is not so very serious also. Okay. But for differential pressure we usually always use liquid filled lines. So, just in order to minimize the pressure fluctuation part. Okay. And what are the other disadvantages of this? Number one is tapping line content. Okay. So, it has to be single phase. Number two is that this tapping line it more or less if it is filled up with the liquid, then usually pumping action is not so very severe. But there are certain other interesting problems here. First thing is, see, in industries when a huge pipe is there and two phase mixture is flowing, in any case two phase flow it is very random, very chaotic. Okay. Along with that there can be some amount of vibration of the test section, the entire support for the test section has been installed, there can be vibrations everywhere when really the flow is going in under industrial circumstances at quite high flow rates. Differential pressure transducer, it is usually designed to measure very low pressures, isn't it? So, therefore, even if there is a Rick vibration also, that also it catches up and it records. This you have to be very careful. And what is the other interesting part here? Other interesting part here is, see, whenever you are measuring pressure difference, I have already shown you here that there has to be an offset. Okay. Now, if you notice that this particular offset, that depends upon your vertical distance between the tapping lines, it depends on rho c. Okay. Now, if the differential pressure transducer is measuring a very small pressure, suppose it is smaller than the offset, then can it record that pressure? Because anyhow the offset is the minimum, that offset occurs even when there is no pressure at all, there is no pressure difference, the offset occurs. So, suppose you have to measure pressures lower than the offset, can the differential pressure transducer do it? So, therefore, the other thing is that the offset corresponding to 0 pressure difference, the range has to be at least that particular offset, and if the pressure that we want to measure, if that is lower than the offset, then in that case we find that we can have a problem in this particular case. Okay. So, therefore, it can be, it has to be selected with a range which is at least equal to the offset value. Okay. If it is less than that, then in that case we have a problem. Now, again when we have problems, we have to find out solutions for it also. What can be the possible solutions? The problem with video lecture is I cannot wait for you to answer. So, that is the problem. So, that is sad in one way, that I should admit. Anyhow, so the thing is, so therefore, this offset, if it is compensated by some means, then in that case the differential pressure transducer, the DP transducer, it can be used to measure pressure differences, very low pressure differences, if the offset is compensated in some particular way. What can we do to compensate the offset? A very common technique is we use a compensating manometer. I do not know whether you understand. See, there is a CCl for water manometer here. Okay. Here the offset is compensated. So, therefore, after the offset, only the pressure difference which is actually occurring due to flow here, that goes to the DP cell, and therefore, we can measure the pressure difference very, very accurately, because the offset has already been taken care of, and so therefore, very low pressure differences can also be measured in this DP cell. Correct? Do you get me? Okay. So, therefore, if we want to conclude, what are the different methods of pressure drop measurement? You already know the methods. One is fluid manometers, usually they are liquid manometers. When we have liquid manometers, they have got their own limitations regarding the range of measurements. isn't it? If we have to go for higher sensitivity, then in that case naturally from mercury manometers we go to CCl4 and so on and so forth. We go for inclined manometers. Okay. For liquid filled cases, it is very frequently we see that micro manometers etc., can also be used for better measurements. Then the other technique, as we have already seen, it is subtraction of signals from two locally mounted pressure transducers, that is there, and after that the differential pressure transducers. It is not always that we will always select that one particular method among these is the best. If you consider all the factors, we can never say that well DP transducers should always be used and others should never be used, or in other words wall mounted transducers should always be used and the others should never be used. We cannot say such things. Okay. So, depending upon our conditions, depending upon the application where we have to measure pressure drop, we have to select a proper technique for it. What are the criteria for selection then? Let us see what are the different ways by which this particular selection is done. First thing is, do you need a rapid response? For example, are you interested to measure the pressure fluctuations or only the pressure drop? Okay. Suppose you are interested to find out the pressure fluctuations, then in that case naturally there is only one thing that we cannot go for manometers. We cannot even go for differential pressure transducers, they are also not accurate. The only option we have is that locally mounted pressure transducers, that is mandatory. Okay. And among these locally mounted pressure transducers also we have to see that depending upon the response time and the temperature, what is the type of transducer that we will select, and whether this transducer has direct access to the fluid or not. If it has direct access, if we need a very fast response time and high temperature or something, we will select some type of transducers, otherwise we will go for something else. But remember, if a rapid response is needed, or rather we would like to record the pressure fluctuations with time, there is only one thing, wall mounted pressure transducers. Usually we try to measure, when we try to measure fluctuations, it is of pressure and not of pressure drop. Okay. So, therefore, it is always wall mounted pressure transducers. Next is, if you need an electrical output, or in other words you want to record the output, from manometer you can never do it. Okay. So, therefore, for such type of cases you have to go for a DP transducer. If electrical output is not needed, liquid manometers are fine. What is the next thing? Whether the tapping lines have to be kept full of gas or the liquid. Now, you have already understood it is better to have tapping lines full of liquid and also to have a liquid purging system. But at the same time, remember, for more accurate measurements, gas filled lines are better if the line content is completely unambiguous, very important, because gas filled lines with unambiguous line content is something very rare. If you can ensure it, if you can maintain it, then definitely gas filled lines are more accurate, but for most of the situations we cannot do it. Okay. So, therefore, this has to be remembered, and in practice usually we go for liquid filled lines. What is the other thing? Is the channel fluid condensable or evaporable? Okay. So, in that particular case, what do we do? Suppose we are working with cryogenic fluids. What can we do? In the tapping line, just after the tapping point, we can install an evaporator if it is gas filled or vapor filled lines, or a condenser if it is liquid filled lines. So, what happens if there is a condenser or evaporator also, if a vapor enters by any chance, that can be condensed to a liquid. But this particular technique is not a very popular one because it takes a lot of time, it is not worth it. Okay, naturally, because for condensation evaporation it takes time. So, this is not a very well favored system, but this can be one. The other thing is, how much accuracy do you need? If suppose you use the final point which I have given is how much is high accuracy required, because if you need high accuracy, then for liquid filled tapping lines we can go for inverted liquid gas manometer types as compared to liquid mercury manometers. instead of liquid mercury manometers, if we go for liquid gas manometers, it is going to be better. And if we have gas filled lines, special cases, we can go for inclined manometers or micro manometers. Remember this, using manometers, if we need a high accuracy, then instead of liquid mercury manometers, we can go to liquid gas manometers for liquid filled lines. And special cases where we use gas filled pressure lines, we can use inclined manometers or micrometers. Another thing which you already know from your single phase, I would just like to remind you, when we use manometers, the other thing is that, for as I was telling you, the manometric liquid can enter the fluid, the pressure line. How do we alleviate that particular problem? If you draw the diagram of a manometer which is usually supplied to you, I do not know whether you have ever noticed or whether you have ever thought why this diagram or why the manometer is made in this particular way. This is usually the manometer which is made. Why do we do this? Because whenever the liquid tries to come up, at least here the level rise will not be much. Okay. So, these are known as catch pots, where the manometric liquid meets the tapping line liquid. Okay. And therefore, these catch pots are there to prevent the, or rather to minimize, it cannot prevent it, rather to minimize the bigger catch pots you use, the better it is. It just minimizes the ingress of the manometric liquid into the lines, so that the consequences of this particular ingress can be minimized. So, this completes our discussion on the challenges which we face for measuring pressure drop under two phase flow conditions. Tomorrow we will be taking up the measurements of void fraction, and then we will be taking up the different ways to estimate the flow regimes. Thank you very much.